All right, let's get going. Any questions? Projects going well? When are they due?
Next Thursday.
Right
Can you
on.
come in this weekend?
What's that? Can I come in this weekend? Why would I need to do that? Are you saying the instruction's been poor and you need help?
No, I mean, just in case we have extra.
Yeah, let's
questions.
decide on Thursday, shall we?
Okay, I won't be
Okay, then if you don't have your voice, then, why won't you be here?
here. So I was
Okay.
the company should
All right. Let's talk about no other questions. Nobody else has homework to turn in? Okay. So before we do that, just so you know where things are going, did everybody see the homework assignment due Tuesday, April 26th? So that's 3 problems. That's the last homework assignment. I know you're probably disappointed, but the following week is, well, dead week, right? And what does dead week mean? No, it means you're not supposed to give final exams during that week. You can still have homework, you can still have quizzes, you can still have the same thing, but what they want to avoid is people giving the final exam to get out of school early. So that's what dead week is. So we'll have the final exams the following week, okay? Did you know that? Okay, so I also tend to want to give you a little break from my class. Since your projects will be due on the 28th and your homework's due, then basically the last week you're like, yeah, this is nice. No homework due, no project, life is good. And then you can study for the final, and right? So no more homework after this. But I have to ask, is anybody feeling ripped off because of that? Like you didn't get enough assessment? Adam wants a couple more. I think we should have homework due on the day of the final. That would be, I'd get a reputation then.
Can we have 2 finals?
2 finals.
One isn't enough.
You know what? Another project sounds about right.
And you get to take the score that's the lowest score that you receive. All right, so we're going to go through compensation today. As usual, oh wait, does anybody have any project questions? If you need me to come in this weekend, oh wait, I can't come in this weekend, I'm traveling. So, oh well. All right, so if you have project questions, we can answer them on Thursday.
I'll give Cass my project questions.
Oh, that's right, you're not going to be here. All right, so we'll go here now. Let's call this the in. Has anybody ever seen this before?
Yeah.
Did we see it in this class? So you all know this, you're going to be able to help me real quick. What's this value here? Beta V out. What's beta called? What is beta? How much of the output is fed back and subtracted from the input? The feedback factor. Does everybody follow that? What's this value right here then? And what's this value then? And what's that equal to? Yay? Seen it before? Or AOL times VI equals 1 plus AOL beta times V out. Or last but not least, V out over V in equals AOL divided by 1 plus AOL times beta. Is everybody cool? Okay, so give me an example of a circuit that implements this. Yeah. Notice that when AOL beta goes to -1, what happens to the denominator? Blows up, right? So let's go ahead and do this for the op amp, we have the following. I'm going to call this V fed back. And this has got a gain AOL, and so this voltage here is AOL times V in minus V fed back. Does anybody disagree with that or not seen that before? Now I'm going to put a box around here, and this voltage is V out times R1 over R1 plus R2, and that's equal to V fed back. So what is beta? Right on. Okay, if AOL goes to infinity, what does this go to? So divide top and bottom by 1 over AL. If AOL goes to infinity, what does this go to? Let's make it easy on you. If AOL goes to infinity, what does this equal? 1 over beta. So the closed loop gain, which this is the closed loop gain, V out over V in, infinite open loop gain goes to 1 over beta. So I go back over here and I ask, oh wait, what does it mean when I say closed loop ideal? That's V out over V in. And what is the requirements there? And that's equal to 1 over beta, which equals oh, but wait, we have that memorized. That is the equation for the non-inverting op-amp topology. Does everybody follow that? Any questions? So now, I'm going to go back and I'm going to write the closed loop gain without infinite gain, open loop gain. Remember, if I said if AOL is 100 and your beta is given by this, calculate the closed loop gain. Remember, we've done that. And we can just use this equation to calculate what it is. Any questions? All right. So now, what is the maximum value that I can have for beta? What's the maximum amount of the output that I can feed back? Yeah, all of it, right? So V out being fed back to VF, if I feed all of it back, I mean, unless I put an amplifier in there or some peaking, is V beta is equal to 1. All of the outputs fed back. So for beta equal to 1, what is R1? For beta equal 1. For beta equal 1, I'm sorry. If I want, for my closed loop, then what would this 1 over beta max, what is the closed loop gain? 1. How do I get a closed loop gain of 1? What is R1 for a closed loop gain of 1? Infinity. What is an infinite resistor? What do I do with R1 there? Yeah, just remove it. Does everybody follow? Doesn't matter what R2 is, but why should I waste money on a resistor? So I'll generally put R2 as a 0 or just a short. Does everybody see that? Questions? So if I know that for instability, AOL times beta is equal to -1, or let's write that a little bit more like we're used to, the magnitude of AOL beta is equal to 1, and the phase of AOL beta is equal to 180. What's the maximum value of beta? 1. So if I'm designing a general purpose op amp, I can set beta equal to 1 and simply look at when AOL is 180 and the magnitude of AOL is 1. So we're going to look at that as an indication of stability. Questions? Okay, if closed loop gain is 2, what is beta? One half. If the closed loop gain is 10, what is beta? 1/10. So wait a sec. If I make beta smaller and smaller and smaller, that means it's easier for me to have a stable amplifier. But wait a sec, if I can get higher gain and still have a stable amplifier, why do I use feedback? What's the point of using the feedback to begin with? Okay, so feedback's great. If you look at an op amp and the gain was 10,000, 20,000, 30,000, once you use feedback, you can set the gain to a precise value, the ratio of the resistors. Okay? The problem with using feedback is stability. So the more you feedback, or the fact you're using feedback, you have to deal with the stability of the system. If you don't use feedback, you don't have stability problems because nothing's feeding back and possibly adding to the input. And everybody understands that when the phase shift is negative and I'm feeding back something that's 180 degrees out of phase of this is no longer a minus, it's a plus. So if this was going up, and this should be going down, but because of the phase shift through the op amp, it actually goes up like this. They're going in the same direction. They add to each other, right? No, instead of subtract, this would go down, this would subtract, or go up, I guess. This would go up if the phase shift is 0, and they would subtract to 0. This would go the other direction. The polarity would change, and we'd think of this as a positive signal. So let me ask some questions. For the basic equation here, where does instability occur? When this goes to -1 and the denominator goes to 0. AOL beta going to -1, the worst case, unless you have an amplifier in the feedback path, is when beta is equal to 1. All of your output is fed back. If that's the case for general purpose op amp design, I use AOL equal -1 and AOL equal plus, the phase of AOL equal plus or minus 180. If I get a job and I'm designing an op amp for a circuit, and I know that that circuit's always going to have, it's on a chip, so it'll always have a fixed gain of 10. What do I use for beta then? 0.1, 1/10. Then AOL can actually be higher. And I can design my stabilities much easier to maintain because I'm only going to use that op amp in a gain of 10 configuration. I'm only feeding back 1/10 of the output. I don't need to design for beta equal to 1. But in the chapter we're about to do, we're designing for general purpose op amps like you would use in the lab. You'd get a chip, some student or some engineer would come and they would take the op amp and they would put it into some configuration. For your design, in your project, what is your beta? 1. Well, it's a buffer. All of the output's fed back. Beta is always 1. Any questions? Does it make sense that how to go from here or to go here to here? What each block diagram is? What's AOL? Open loop gain of the op amp, which is defined as the ratio of V out to V in minus V plus minus V minus. Right? How do I get the difference? How do I get this? Diff amp takes a difference in the inputs. How do I get the feedback factor? Resistors. No magic. Everything makes sense. Okay, so now let's take our basic topology. Let's take our topology, the two-stage op amp, And I've added here, first off, assuming everybody's read the chapter and we've gone over this last time and other times, does anybody have questions on how this topology is designed? Notice it can only drive resistive loads because if I put capacitive loads, because if I put a resistor here, it kills the gain. Okay, so now, here's the issue. Let me tell you problems, and you'll waste time if you don't understand what I'm about to show you. So I'm just going to use the triangle symbol for the op amp. So I draw these. What are these 2 points correspond to in our circuit? Yeah, the gates of the diff amp, right? The two diff pair. Okay? So let's say I do the following. And we are using the C5 process, so I do 2.5, and I short these two together, and I say, what is the output? And you can try this in a sim, and let me just put on here. Well, if I look at this, and I'm using a simulation, everything is perfectly matched. These two are at 2.5. Got the same current flowing through both sides. This is twice the width. There's two of them, 100 by 2. This voltage and this voltage are exactly the same. This current's going to be biased to have the same exact current as these two. However, the source to drain voltage here is going to be different than the source to drain voltage here. The source to drain, or the voltage across M8 here, is going to be different than the voltage across M6. So there'll be a slight variation in the current in this one versus the current in this one. That'll cause the output, because you have two current sources basically in series, that'll cause the output to move towards VDD or to move towards ground. In other words, maybe if you get lucky, but I'm pretty sure you won't, this won't be at 2.5 or some known voltage. It'll be at something close to VDD or close to ground. Does everybody follow? That doesn't work. If this goes close to ground, this starts to shut off. It no longer behaves like a current sink, and so your gain drops. So the question is, how do I bias this up so that it works well and I can look at the AC gain in a simulation? The way I'm going to do it is the following. I'm going to put 2.5 volts here. Now what I want to do, I'm not putting it in a closed loop configuration. I'm just looking at the open loop response. Put 2.5 volts there, and now I need to DC bias the minus or inverting input. So I'm going to put a big capacitor here. I'm going to put a big resistor. So for DC, what happens? We know these two voltages will be approximately the same, but not exactly the same unless we're lucky. So this would be 2.502. Well, what's the voltage here then? 2.502. Why? There's no way for a DC current to flow in the capacitor, right? So both sides here have to be the same. So it biases up to what it needs to be to set the output so that the output transistors, this one and this one, these are all biased in saturation. Everybody follow. So this is a DC stability. Okay, for AC though, and I don't want to make this too big because I might get some DC current. I don't want to make it a tera-ohm or something like that. But for the C5 process, you can probably go as far as a gig. Okay, you might put 100 meg and 1, not 1F. For AC though, what's the time constant flowing back for any signals flowing back here? Time constant of 0 would be a wire. Be 100 million seconds. It's a really long time. Very little AC signal here is going to flow back to this node. Does everybody follow that? Okay. So what if I try, first off, let's say I do a transient simulation. Does this work to see, and I put an AC signal here, 2.5, and say millivolts or microvolts in the simulation. I try to do this for an or a transient simulation. Well, the problem is, unless this powers up after the .op at the very beginning to 2.52, you have to charge the output through that huge time constant, and it'll never power up for a transient because it takes too long. So this is good for a .ac. And so we would do the following. We'd put our AC source here. What's the AC voltage here for a simulation? And why? Zero. Why? That's the whole point of this big capacitors, to ensure that doesn't move for AC. If I probe this when I'm doing my AC and I see something there besides nanovolts or something like that, I know this isn't big enough time constant. The AC voltage there is zero. So this is V out. It's going to be AOL times V plus minus zero, because this is zero. Questions? So for AC, it assumes you're using small signals. Even if you don't, you can set this equal to 1. And then when you plot V out is equal to AOL. Does everybody follow that? Because I'm going to do an example. Okay, so let's look at figure 2410. Okay, what's my time constant here? Feeding back. It's 1,000 seconds. Does everybody see that? 10 microfarads times 100 meg. Okay, so now, well, let me ask this. If I keep going lower and lower in frequency, what kind of feedback do I have at very low frequencies? Low frequencies, this is an open. So all of the outputs fed back and beta is equal to 1. So as the frequency starts to get lower, it'll roll off and go to a gain of 1. I'm going to prove that. Actually, let's prove it right now. What is the AC voltage here, VP, though? 1 volt. Assuming nothing is fed back, what is VM? 0. So what is V out? AOL times 1, or just AOL. So I'm going to plot now and look at what we got. And there's my open loop gain. And I'm at about 60 dB, which is a gain of 1,000. I go to 0 dB, which is the gain is 1, and I look, and what's the phase shift? Can you see it all right?
180.
Yeah, it's 180. Oh wait, so if I use this op amp just the way it is, it's going to be unstable. But I'm going to prove that. Okay? But before I do, let me show you something. Let's go change our simulation so that instead of only going down to 1 kilohertz, I go down to, how about 0.01 hertz. And let's stop at 100 meg. I hit run. What's happening here? What's that? This says, hey, your RC feedback for DC stability is no longer not feeding anything back, you're starting to feed signals back. Well, if I keep going lower in frequency, what's ultimately the op-amp's output going to go to? It's going to go to where this behaves like an open, and this all of the output's fed back, it'll go to 0 dB. Why don't we do that and see what happens? Let's go stop frequency 1 kilohertz. Start frequency, how about 1 microhertz? Hey, it goes to 0 dB. He's right. Flattens out at 0 dB. Okay. Let's go now look at what happens if we increase the capacitor. Before I do the time, actually before we even do that, refresh my memory. You see here, CC is only 100 femto. What is the CC used for? Yeah, to kill the gain at higher frequency so the op-amp's stable. But there's not much killing here because it's a small capacitor. In a moment, I'll go back and show you what happens when we go to 2.4 pico. The gain changes. But let's go see what happens here, which is a transient simulation. And I'm going to leave it at 2.4 pico, and let's hit run. And you see the input's a step, it's the green. Actually, let's do this. Pull the output up here. The input goes from 500 to 505. The output goes from 500 to 505, but it get all this ringing. What does that tell me, the ringing? The compensation capacitor is not big enough, or it's not compensated enough. There's the other problem with that 0 that we have. Okay? Does everybody see that? So when I look at the phase shift in the AC and I see, hey, it's unstable, when I look at it in the time domain, instability is seen by overshoot and ringing. And I'm going to put the 100 femtofarad in right now that we had where it was at -1. This is still ends up being stable, right? Okay, but if I go back here and I put in the 100 femtofarad where my open loop gain is 1 with a phase shift of 180, what do you think I'm going to see? I'm just going to see lots of oscillations. It's unstable. Does everybody follow that? If I go back here and I look at what the AC, does everybody get that? So when you're doing your projects, you put in a step response into your projects. If you see ringing, that ringing is going to be an indication that your design's not stable. Okay? So let's go back here and look, and let's see what the stability is here. So I go to 0 dB, which is right about there, and I go up, and I see at 0 dB, I see 160 degrees or so. Does everybody see that? Or maybe 155? I don't know, something like that. Does everybody follow? Okay. Tell me now, if I want the design to be more stable, what do I want this phase shift to do to indicate more stability in the design? Where do I want it to go, up or down? I want it to move down towards 180? No, I want it to move away from 180. 90. Well, I've already got a 90-degree phase shift because I've introduced a dominant pull at low frequencies to kill the gain at high frequencies. So I ideally want this phase shift to be 90 degrees. I want it to move up. Does everybody follow that? Okay, so let me pause for a moment and talk about how you indicate how stable your op-amp is. You see, if I go to 0 dB and I go up, the phase shift is, say, 155. The difference between 180 and what it actually is, in this case 155, is called the phase margin. Here I've got a phase margin of 35 degrees. That's how far away the phase shift is from 180, which I know is the instability part. 35-degree phase margin. Questions? As the phase margin gets smaller, I know the design will get less stable. Generally, you want phase margins for general designs of 60 degrees or more. Why? It's easier to ensure they're stable over temperature and power supply. And we don't get as much ringing. You just saw how much ringing we got with 35 degrees. We got quite a bit. Does everybody follow? So let's play around real quick. We're learning. What's the easy way to increase the phase margin? Let me just comment real quick here. You see how it flattens out? That's the right half plane 0 we talk about. That's bad because instead of the gain rolling off, it's staying around 0, and that makes it worse than it really needs to be. So we'll address that in a moment. But for now, how do I get a higher phase margin? How do I kill the gain or move the gain down? Yeah, increase the compensation capacitor. Let's go to 10 pico. Let's go a factor of 4. And we hit run. And we go to 0, and it's moved to here. And it's a little bit more stable. Instead of being 165, it's now 150, but you see how it's flattening out. So again, we'll address that in a moment. But let's go look and see what that does in the step response. So I run, and I see the step response looks like this. So everybody take a picture of that with your mind's eye, up to 520, down to 485 or so. I go here and I say, let's see what happens if we put 10 pico babies in there. We hit run. And we have some slew rate problems, but if we look just at the rising edge, does everybody see how we get less overshoot? We'll talk about the slew rate problems in a moment. Okay, any questions? So let's do the following. Let's modify this. Let's just play around, and you tell me, well, first off, explain to me qualitatively, what is the problem with the 0 here? Tell me, where does this flattening come from? Well, the right half plane 0, but where does that come from? Well, I'm taking the beatings. Remember, we went over this with the Miller effect. What happens? Well, let's ask this. Which amplifier is doing the inversion for the Miller effect? Well, what are the names of the amplifiers in the op-amp? You say, what is this amplifier called right here? And that's a diff amp. What's this amplifier right here called? Common source. Where is the Miller capacitance? It's from the input to the output of what? Here's the input of the common source. Here's the output of the common source. Remember, we're going to use the Miller effect to multiply this up. So this appears to be a larger capacitance here. Goes directly to the output with the 1 plus 1 over the gain. So this is the amplifier that's having the Miller effect. Where did the 0 come from? Remember, when the input feeds directly to the output without the inversion. So remember, this is inverting. The gate goes down, pulls the output up. The gate goes up, the output gets pulled down through the current source. It's an inverting amplifier. It's this amplifier used for Miller effect. So at high frequencies, the input and output here get shorted together. Does everybody agree with that? So I don't want the input and the output to get shorted together. I don't want, at high frequencies, this signal to feed back through the Miller capacitance. I don't want, rather, the signal here to feed forward to the output without an inversion. Does everybody follow that? Does everybody see what I'm saying? So I don't want the signal here to feed back. So you know what I'm going to do to avoid that? I'm going to do the following. I'm going to play around. If I take these amplifiers, oops, yeah, let's move it over. Okay, it's the same circuit. Did everybody agree? And what I'm going to do is I'm going to cut it right here. And I'm going to try to add a circuit element that blocks the forward signal from here to here, but allows the feedback signal to come back through here. So what I'm going to do is I'm going to put a voltage controlled voltage source with a gain of 1. Just change it right there. 1. I'm going to put a ground here, and then I'm going to put a wire that goes here. Okay, so for low frequencies, this voltage and this voltage are the same. Or for all frequencies, this voltage and this voltage are the same. Would everybody agree? However, now at high frequencies, the signal here can't feed through to the output over here because I blocked it with this voltage controlled voltage source. Does everybody see that? So if I have a wiggle here, how does it get over here? It can't. But if I have a wiggle here, by definition, the voltage controlled voltage source will be this voltage minus this voltage times the gain of 1. So this voltage will always go directly over here. Does everybody see that? And what I'm claiming is that this flatness will go away now. I'm getting rid of the 0. No, that's a little bit different. We'll cover that in a moment. The shifting to left half plane is blocking at high frequencies by changing this resistor. Okay? This is just showing you that I can get rid of it by blocking that path from here to here and only having the reverse path. Okay, so now when I hit run, what do you expect is going to happen? That flat area, this step's going to go away because I'm blocking the feeding at high frequencies from the input of the common source to the output of the common source. But let's find out. Whoa! He knows what he's doing. Does everybody see it's gone? Let's see what our phase margin is now. We go to 0 dB and we go up. Whoa, 90-degree phase margin. Life is good.
So we can use that in our projects, right?
No, you can't use a voltage controlled voltage source. So now, let's go back and open up before I close this because I'm lazy and I don't want to retype everything. And I hit the run button in our circuit and I see the ringing. Now I come back over here and I hit copy, and let's just plop this down, and I come over here, I plop that, and I can close all these, and then I can stretch this out. Get the scissors out here. And then I hit run, or I hit this. I think that's the same thing. And I look at that and I go, okay, from there where I've got the 0 to, did they rename the node? VL? Yeah, we'll fix that. Oh, yes it did. All right, let's just stretch that up. Get out the scissors here. And then go from here. Oh wait, that's done. We're done, that's it. Hit run. Oh, there's where it went. All right. Now let's try it. Boom. Whoa, look much better. So anyway, the whole point is that 0 is a pain. Okay, any questions? Yes?
So our project, we don't have loaded to register too. Then when you loaded register, it's gonna change also.
Loaded register?
No, register.
Load resistor, yeah, because you have to have a buffer on the output. So you can't use this topology by itself, right? Because a resistor here will kill the gain. You have to put a source follower or some other buffer to isolate gain from the resistor. Just like we discussed last time. Any other questions? Yes?
For increasing that resistance due to the compensation capacitor, is that kind of to like dampen it? Basically,
No, we're going to go over that next. Alright. Okay, so let's close this. Let's go back up. Alright, so now, oops, let's make sure we write 2 on this. Alright, so now, when I look at the design, well, let's actually look here at the book. I can block that forward path. Here's one way. This way, the signal from the output goes back through to the node 1 through the source follower. So this is exactly what I just went through, but using transistors. So this signal still gets fed back, but this signal, when it goes forward, goes to VDD. It doesn't go to the gate, right? So the signal, the current goes up the VDD. So one thing else I can do is I can put a resistor in series with the compensation network. And we derived this in chapter 22, I believe. And if you look at the gain stage, and we call this RZ, if you look at the equation in, I'm going to go back to chapter 22 just to prove that we did, or chapter 21, just to review that we did do this. And this is equation 21.73. And if you look, our 0 now will move to 1 over 2 pi c sub c times 1 over gm2 minus rz. And we'll call this 2 gm2. So if I put rz equal to 1 over gm2, then fz goes to infinity and it no longer influences everything, right? Now, in reality, you're not going to be able to cancel everything perfect. But just out of curiosity, for the table 9.2 in this op-amp we just looked at, what is the transconductance of that PMOS? 150 micro. And what's 1 over gm then? 6.5 K. So let's go back now. Yeah. So if this is equation 2173, if you make R's equal to 1 over GM2, 0 will get pushed out to an infinite frequency. And you can actually make this positive and it'll push the 0 into the left half plane. Now there's some other issues with that are, I mean, it's impossible or challenging to make them perfectly match with process and temperature and voltage, so that's one issue. There's also secondary effects that come into play, but let's go back to our schematics that we were just at. And let's go to 24, what was it, 11? There's our 2.4. Let's change this to 6.5 K. Actually, before we do that, let's hit run. Does everybody see the 0? Looking good? Then I go over here and I change this to 6.5 K. Hit OK. Hit run. And now I look and you see, hey, At 0 dB, I've got about a 90-degree phase margin. In fact, you can see that the pole actually moves a little bit in the left half plane. How do I know? Looking at that. Yeah, the phase shift starts to go up a little bit, which is the way we're used to most zeros, right? The zero normally, like in a passive RC circuit, you cancel out that secondary effect, so it no longer starts to flatten out, but also the phase shift starts to go up a bit. Does everybody see that? Okay, so if I go back and I look at the next schematic here, which was the step response. Whoops, I'm getting ahead of myself. Which is the step response. And I say, okay, well, I proved that was because of the zero. What happens if I put this pole or this resistor at 6.5K? I go from this to this. Okay, so now, explain to me why. What's going on? I mean, you're going, oh yeah, it makes sense. Why? Why is that happening? Okay, you always start with what's the issue. The issue is that at high frequencies, this node gets shorted to this node through C sub C, bypassing the inversion of the common source amplifier. By sticking in the resistor here, I'm now attenuating the signal at higher frequencies as it goes from here to here. Wait, but at low frequencies, the impedance that I have here is still dominated by the capacitor, and this doesn't influence anything. Everybody understand? I don't want you just like, oh, I put the resistor in there. Why? Because he said so. Yes.
And two is sizing, Rosie. So you size it based on the GM of what you're connected to.
Yeah, you size it based on this GM.
Okay.
Okay, but I'm going to give you a better way of doing things, all right? Because if you go through and I look at this and I change the power supply, let's say I go to 1.1, we'll see how it works. Should work fine, right? I mean, the input's still going from 5 to 0.505. So I hit run, and I see a little bit of an offset. It seems okay, but in reality, I can't adjust this value. And there's a more important reason. If I use the technique I'm about to show you, I can reduce this capacitor size and remove the zero. If I reduce the capacitor size, what is the benefit of that? So if I go back to, let's just use this circuit. If I reduce this 2.4 to 100 femto, my unity gain frequency, is, we've derived this, my unity gain frequency, my op amp is GM over 2 pi C sub C, where this is the GM of the diff pair. You have some requirement in your projects to get some speed, right? I don't remember what it was, but some unity gain frequency. 100 megahertz?
That's our panel. Yeah.
Okay, so for a unity gain follower, that will be the unity gain frequency. So let me ask this. If I meet the spec and I put in a 1 volt signal into your projects, and it's at 100 megahertz, what do I expect to get out if it's right at the spec of a bandwidth of 100 megahertz? What should the output voltage be peak if the input's 1 volt? So I do the following. What do I expect to get here? If I'm right at the spec where the bandwidth here is, what do I expect to get here? 0.707 volts. Because at the bandwidth, it's 3 dB down. So if you do your projects, you're going to waste a lot of time if you put in 1 volt here and you try to get 1 volt out here. Even though you may be at 120 megahertz bandwidth, it's still not going to be 1 volt because it starts rolling off, right? Okay. So the point is, if I can reduce my C sub C here, I can push out the bandwidth and I can get better performance. So I'm going to do that. I'm going to do that with this topology, and I'm going to do it in a way. I'll draft the schematic so you can see. But before I do that, I want to remind you of something. If I have a transistor and it is, what's the size we're using? 2.5 microns by 100 nano. And you can imagine, if you've taken 421, you can imagine the layout of this, all right? That I can write as the following. Let's just ground this. Does everybody agree these are equivalent, electrically equivalent? However, I know this guy will always be in triode. I can prove, or off. I can prove that this one will always be in triode. But it doesn't matter for what we're doing. The fact that I can split the transistors up and inject a signal in here instead of connecting to here allows me to block a forward path. Now let me discuss that in more detail by using simulations and showing you. Everybody cool with that? Okay. Let's go open up our friend the schematic that rings. Actually, let's do it on this one. Does everybody see this one's unstable? Oops. This one is unstable, right? We're at 0 and 180. Okay? I'm going to use that to block the forward path. And here's what I'm going to do. I'm going to get the scissors out. I'm going to grab this. I'm going to pull it up. And I'm going to copy. Or whoops, let's not do that. Let's do this first. Let's change this width to 50. And this width to 50. Let's get the scissors here. Let's get rid of the resistor. Let's still tie this over. And then let's get the copy function here. And move this over. Oh, okay, it did work. And then let's do the following. So what's this equivalent to now? The two gates are tied together and I've made the L's 50. That's exactly the same thing as I had before. Then I'll do the same thing over here. Except I'm going to move this gate like this. Right? And why don't I, just for the heck of it, show you that we get the same frequency response. 1 ohm resistor is not going to do anything, so I'm going to leave that out. So why don't I just hit run. And I go back to 0 dB. I go up. Does everybody see it's the exact same thing? Okay? However, now I'm going to connect the compensation and inject the compensation current back into here. What does that do? For low frequencies, it doesn't do anything different. Okay, but for high frequencies, when I try to take this node, or I try to have this signal feed forward to this, this is now a triode connected transistor and keeps the gain low. So instead of going from here to here where the gain is high, I'm going from here to here, and so I can still get the current fed back from the output and summed with the current in this diff amp. So let me repeat myself so you don't think I'm up here going womp, 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 womp. Okay? So for low frequencies, this guy's, the output's wiggling around. That injects the current back in here and kills the gain. Does everybody see that? It sums with the current flowing in the transistors. You can convince yourself. For high frequencies now, however, this node doesn't swing very much because it's not a high gain node like this node. This is a high impedance node. It's connected to drains and a gate. This isn't. This transistor's in triode and it's connected to a source, so this is not going to swing a lot. So I'm blocking the shorting or lowering the shorting of this signal to this signal. Okay, so now let's see what happens with the frequency response. So notice 0 dB or a gain of 1 and 180 degrees unstable. I hit run. Now I go to 0, and what's my phase shift? About 130. Much better. And I go, and I did the calculation in the book, but I go here and I say, well, what happens if we go to 240? And the reason I use 240 is that compensates for a unity gain frequency of 100 megahertz. So you'll see the unity gain is at 100 megahertz. Wait, how did I calculate that? 240 femto? I plugged and chugged. Put 100 megahertz, 150 micro, 2 pi, and solve for C sub C is 240. So then I hit run, and I'm going to see the 0 dB is now at 100. And I go to 0 dB. I'm off a little bit. It's at 200. That makes me wonder, did I not calculate it right? 2.4. Let's see. 240 femto. That's right. Should be 100. Oh, it is off a little bit in the book too. All right. So it's a little bit higher than what we calculate, but does everybody see the phase shift now? All I did, and you should do this in your projects if you're using a two-stage op-amp, is you split lengths for the current mirror load. Now life is a lot easier. Yes?
If we split it even more,
Uh,
or would that just make it?
I don't know what you would gain because you're just blocking the path, so I think this is all you need to do. Yeah. So I want to show you what the step response looks like now. Does everybody understand? Now it's nice and stable. I go to 0 dB and I go up and I'm almost at 90 degrees. Okay, so let's go open the step response one, which was right here. And let's get rid of these. And let's get rid of this. Let's hit copy for this stuff. Go back over here. Get rid of that. You want to save changes? Nope. All right, do I need to do anything else? Yes, what do I need to do? Need to connect this back. Oh, I should have run the sim so we could see the difference. Oh well. Now hit run. Oh wait, what's going on there? There's a little bit of an offset, right? How much is the offset? About a millivolt. That bothers me. I don't like offset, but it's there. We talked about that. So what I'm going to do is I'm going to say, well, what happens if I go to 550? The offset's going to be exactly the same millivolt or so, but because I'm stepping 50 millivolts instead of 5, it's going to seem smaller. Does everybody see that? Does everybody remember how much it rang before? You see it's not ringing now, right? Any questions?
How would you fix that?
How do I fix it? You see this transistor's not split length.
You'd split into that one.
I'd probably split length. Let's find out if it works. Because you want symmetry in your design. So you'd go copy this. And then you'd come over here. See if I can get it without connecting. Like that. Let's see what happens. Yay! Even though they behave the same, there's something slightly different, right? Okay,
So we-
is that good?
Yeah.
Okay, so I want to cover one real quick topology that's very useful for this output. Okay? Instead of using, so you could have a diff amp, a common source, and then a source follower. I want to give you one design that's a little bit different that you can use so you don't need a source follower, that the output can drive a resistive load. Okay? So I'm going to go ahead and stop this and go back in here, and then we'll quit. Okay, so you're going to help me. We're going to sketch just what we had before, and since we only have 10 minutes left, I'm not going to sketch the split length devices, okay? So here's the diff pair. This output should be at VSG. Does everybody agree with that? And so I'm going to do the following. And we'll just put this since we're running out of time. And I'm going to go over to here, and we'll see if this makes sense. So what I'm going to do, I'm going to take and put a transistor like this to a bias source called V bias 1. Let's just say V bias P, since I won't want to have lots of bias voltages, and I can get that from the beta multiplier. Then I'm going to come over here and I'm going to put an NMOS in. I'm going to put a PMOS in. And then I'm going to put another current source here. I'm going to V bias in. And you say, hey, wait a sec, you got two current sources fighting each other. And of course, maybe I should draw this as this, just so it's not. But remember, through the feedback, I'll adjust how much current is sunk down here to equalize the currents. Okay, so now, if I ask you, what is this voltage here? VGS. What is this voltage here? Okay, so what if I go and I take the, okay, so these are constant, right? I've got constant currents through here. What if I take and I do the following? I go to a and I ask, what is the total voltage between here and here? Oh wait, won't that then bias these and I can make these bigger? So if there was 10 microamps flowing in these and I had these as M equal 100, wouldn't there be 100 microamps, or I'm sorry, M equal 10? I was getting ahead of my thought process there. Wouldn't there be 100 microamps flowing in there? So let's see, if this is V out, and this node goes up a little bit, what happens to this node here and why? It's got to go up the same amount. I've got, these are just batteries. I can think of these as just batteries. Right? Does everybody agree with that? So if this node goes up a little, this node's got to go up a little. Does everybody see that? If they go up together, that causes this guy to turn on and this guy to shut off. Yay? And if I go the other way, then this one shuts off and this one turns on. But tell me what the issue is. What's the gain from here to here? Voltage gain. Inputs on the gate, outputs on the source. Inputs on the gate, outputs on the source. What kind of amplifier is that? Yeah, it's a source follower. Inputs on the gate, outputs on the source. What's the gain of the source follower? 1. This has a gain of 1. But wait, I can put a resistive load there and drive it, can't I? Okay, but there's no second stage gain, so I've got issues with getting high op-amp gain. But if I do that and I use these transistors, I can drive a resistive load. What's the output swing max? What's the maximum voltage I could get to here? Right? This can go all the way up to VDD minus VSD sat. What's the minimum voltage I can get right there? Just VSD sat, right? These can swing. So what's the output swing to? This voltage minus VGS. What's the min output swing? VDS sat plus VSG. So I've got limited swing. But this still might be good enough to meet your specs. And this is called Class AB because when I put a pulse in, you can actually get one side to shut off. That's the Class B. But in normal operation, it's operating Class A because there's current flowing in both transistors. Okay, so now how would I modify this to use this section with my basic op-amp that I discussed a moment ago? Here, let's sketch it. Let's sketch it the following. Here, we can do it on this schematic. Just stare at this schematic and tell me. Let's get rid of these so you know those aren't there. Those were just to illustrate those behave like a battery. Tell me how to tweak this schematic so I can use this output stage. Simple, simple change based upon what you know, what we did earlier. How do I get gain? Well, I can't go to this stage directly, right? Because then it's only the gain from the input of my diff amp to this node, and then the gain from here to the output's 1.
So would you put in your gain and then connect the output gain to the where that is?
Okay, so I can tell you, do two things. Cut and connect. Where do I cut? Boom, right there. Where do I connect? Boom, right there. Wait, this is exactly the same topology, except now I have a gain from here to here, which is node 1. And then I've got a gain from here to here, which is node 2. Where do I put the compensation capacitor? Node 2, back to node 1, and through the split length device. So let's see what I've got. I've got high gain with the two gain stages, because this is still a current source load. These just behave as batteries. Then I've got an output buffer that's going to provide the ability to drive a resistive load. So let's throw some numbers in and then quit. Okay, I'm going to write, and let's write it on page 5 here. I'll go back. The output max, and let's use a different color, equals VDD minus VSD sat minus VGS. VDD minus VSD sat minus VGS. Does everybody see that? V out min equals VDS sat plus VSG. VDS sat plus VSG. So let's, even though it's table 9.1 and has nothing to do with the design process, let's just throw some numbers in there using table 9.1. Again, it's not the same numbers as you'll get in your projects, but they could be similar. Okay, so what is VDD? 5. What is VSD sat? What is VGS? So what's the maximum output swing? Okay, it's actually going to be a little less than that because these will have body effect. But here, what is VSDS sat? What is VSG? So your output can swing with that topology between 3.7 and 1.4. I don't remember if that meets your spec or not, but that's one possibility of an output buffer. When we come back, I'm going to give you another possibility for an output buffer for your projects, but you should be getting a topology together, have your design so you know what your overdrive is, document what your FT is and how you selected overdrive using your L's. Notice if you're using minimum L, that on your devices here, for the PMOS, whoops, where is it? Oh, I didn't draw it out, but for the devices here, you might have to split them up so that you can inject the current. That's fine, as long as you know what you're doing. Any questions? Have a good day. We'll see you on Thursday.